morning, good afternoon, and good evening. Thank you for joining Apache Beam Day on Google Open Source Live. This is a monthly series of sessions led by experts from Google and community leaders. We really appreciate everyone taking the time to come here digitally to learn more about Apache Beam. My name is Samuel Rodi, and I'm a software engineer working on Google Cloud Dataflow in sunny Seattle, Washington.
And I'm Robert Burke. I also work at Google as a software engineer, working on the Apache Beam Go SDK. I'm located in rainy Seattle, Washington, and I'm excited for you to learn about Apache Beam. For those of you new to Apache Beam, it's a unified model to write both batch and streaming data processing pipelines. This allows you to write portable pipelines once, and then run in a number of different environments, like Cloud Dataflow, Apache Flink, and Spark, just to name a few.
If you're looking to learn more about Beam, you're in the right place, as we have some really interesting topics today. We'll kick it off with a talk from Inigo San Jose, walking us through the life of a Google Technical Solutions engineer, and speaking about distributed data processing with Apache Beam. This presentation is it's a great overview and introduction to Apache Beam, going into some specifics, some generalizations, and kind of a broad overview about how Apache Beam works. Next is Boyuan, talking about the new data source API that allows for more expressive batch and streaming reads. Before this, we had something called the custom source API, which was not very expressive and led to some very cluttered and buggy sources that were in Apache Beam. And so this new Splittable DoFn API will allow you to optimize your sources and write it in a more clean way. Then next is Alex Kosalapov from Akvelon about how they use Beam with Dataflow templates. Finally, we'll wrap it up with William Sykes from Wiseline describing building Beam pipelines with CDC and Debezium.
Before we hand things off to our first speaker, though, we have a couple of housekeeping items. Don't forget to put your questions in the live Q&A forum below the live stream window. Speakers are ready to answer your questions live. If you're viewing in full screen, you'll need to exit full screen to see the live Q&A forum. Our sessions have been pre-recorded to allow for accurate transcripts, and so speakers can focus on answering your questions live. We would love to hear your thoughts on these sessions, so feel free to make comments in the live forum. Once we're done, don't forget to join us all at the after party on Google Meet. We will share a link to Google Meet at the end of the last session. Oh, and last but not least, use the hashtag GoogleOSLive to share your experience on social media.
And with that, enjoy.
Hi everyone, I'm Inigo San Jose. I'm a technical solutions engineer at Google, and I'm very, very happy to be here with you kicking off Beam Day. And of course, I'm going to be talking about Apache Beam, which I hope is not a surprise for any of you. And the agenda for today is we're going to start talking about Apache Beam, what it is, and what is its model, what's the business proposition that it has, and we're going to end with one demo. So let's start with what's Apache Beam. So Apache Beam is an open source data parallel processing model that works both with batch and streaming, and it can be used in different distributed processing backends. And you might be asking, what's the difference between Apache Beam and other data parallel processing engines? So here it comes, the Apache Beam model. There are three main things that make Apache Beam different. The first one is that it's unified. We have a single programming model for both batch and streaming. It's portable, so it can be executed in different execution environments, and it's extensible. So we can write and share new SDKs, IO connectors, and transformation libraries. What do we exactly mean when we say that Apache Beam is unified? This means that for both batch and streaming, the SDK is the same. So if we write something in batch and we want to move it to streaming, we don't need to change the code. We only need to add some standard logic that comes from from streaming because we need to use unbounded sources. This can be adding windows or splitting the bounded source in different chunks of bounded data. So an example of this could be if we have some batch pipeline that uses a map or uses a flat map, we don't really need to change anything from it to streaming. The same exact code will work from one to the other. And the same with a group by. If we're adding a group by from batch to streaming, we only will need to add these windows that I mentioned before. Apache Beam is portable, so we have different SDKs, different languages that you can write your pipeline in, and you can run this pipeline in different runners. So for SDKs, we have Java, we have Python, Go, and SQL. And for runners, we have Cloud Dataflow, Flink, Spark, and we can even run it in our own computer via Direct Runner. And the advantage of this is that you can use the same pipeline that you wrote in Java, Python, or whatever SDK, and you can send it to different runners without changing pretty much anything from your code. So you only need to change the options that are used to reach this execution engine. For example, if you're using Cloud Dataflow, you need to add a project that is going to be the project in GCP that the pipeline is going to be running. But if you use Direct Runner, you don't need to change anything with these options. In this example, we have a sample key. As you can see that the logic in Java, Python, and Go is pretty much the same. SQL is of course a little bit different, but this is expected. So I want to explain you how this flexibility came. And before doing that, I want to start explaining a bit of the Apache Beam history. At the very beginning, there was only Java and some runners, and we needed a way to translate from Java to the other runners. So there was a specific way to translate from Java to Dataflow, another way from Java to Splink, another way from Java to Spark. And when new SDKs came, this approach wasn't the best, of course, because we will need a way from Java to Dataflow, another way from Python to Flink, another way from Python to Spark, and this doesn't scale. In case that we wanted to add a new SDK, we will need to create a lot of translations between the new SDK and all the runners that we have, and the same in case we wanted to add a new runner. So the Apache Beam team came up with this idea. So on the top, we have the SDKs, Java, Python, and Go, and in the middle, we have the runners. And in between those, we have something called the Runner API. This Runner API, what it does is translates from Java, from Python, or from Go to an abstraction of those languages, which we actually use protobuf, since it can be read from pretty much all the languages. And this abstraction gets sent to our runner, which they read this pipeline and actually know what they have to do. And between the runners and the pipeline execution, we also add one layer. This is the Fan API. This Fan API is also needed because we need a standard interface to connect from our code to our execution engine. And we didn't want to do this for every single language, for every single runner. Let me show you a bit how this works. What's the schema of all this? We have in red everything that is language specific, and in green everything that is language agnostic. So we have our Beam application in whatever SDK we want it, and this Beam application gets sent to the job server via the job API. Then this gets sent to our runner using the Runner API. In this case, we're using Flink as an example, but of course the same will apply for Dataflow or for Spark. Flink, our runner, gets different tasks assigned that it needs to execute. In this case, we have an executable state, a group by key, and another executable state. These executable stages connect to an SDK harness via the Fan API. These SDK harness are the pieces of the runner that actually execute the user code. And they tend to be Docker containers, but they don't actually have to be. They can be embedded within the runner itself, or they can be an extra process within the runner. And apart from the flexibility that using this Fan API and this Runner API give us when it comes to adding new SDKs or adding new runners, it also provides one very nice feature. This feature is called cross-language. So let's say that we have our Beam application written in Python, and we want to use Kafka.io. Kafka.io is an IO that has been around in Java for a long time. It's very well tested, it's very mature, but it's not so much in Python. So instead of having to write the Kafka IO in Python again, we can use something called expansion service that connects these executable states with a Java harness with the Fun API. So we will be able to execute this part of the pipeline with a Java harness, and the rest of the pipeline can be executed with Python. We can see that after the first executable states with Kafka IO, we have another executable state, that goes to the Python SDK harness via the Fun API. And we can see that we have two steps there, Pardue and assign window. This is another optimization that happens with this Fun API. Instead of having to create one container for every single step, so one for Pardue and one for assign window, we only need one of those. We combine them together, we combine all the steps, and we only need this container. And finally, Apache Beam is very extensible. So we can create new SDKs and new runners. One example of those is SCO, which is an Scala SDK written by Spotify, and also is very customizable. So we can create custom sources and custom sinks in case that one of the IOs we need is not yet available in Apache Beam. Let's say that you need to read an in-house database and we don't have any IO available there, you can create your own source and sinks. And in case you want, you can of course share it with the community. And also Apache Beam is highly customizable. We have a Pardue, which is a generalization of map and flat map that allows us to control the elements better, sending the elements to different P collection as we want. And there are other things that we can customize, for example, custom windows. With this, let's head off to the demo and see you there.
So here we are in a JupyterLab notebook, which is the environment we're going to be using for this demo. And the idea of the demo is to show you how it is to change from one runner to another, and how it is to change from batch to streaming, just by adding this standard logic that we mentioned before, like adding windows or another way of splitting unbounded data into bounded data. The example we're going to be using is a word count, which is the hello world of the ETL pipelines. So let's get into it. Let me first import the things we're going to be using for the demo. And I'm also going to be importing some variables. These variables are going to be used to reach my project in Dataflow. So now we have the actual pipeline. And since we're going to be using the first example, interactive runner, we don't need to add any options the same way we don't need to add any options when using direct runner. Interactive runner is a specific runner made for notebooks that provides some extra visualization, and it's a good fit for this demo. So now it comes the actual business logic for our pipeline. We're going to be reading from a public bucket that contains a text file, which is the play by Shakespeare King Lear. So in order to read from this text file, we're going to be using read from text, and let's point to this path. Now, when we read from text, using read from text, the output is going to be every line that the file contains. And we need to split that line into more than one word. So here it comes the actual word count. So let's do count source. And since we're outputting more than one element for input element, we need a flat map. So let's do now split words. Now, if you check the split word function, you can see that we're actually outputting key values. This is because we're going to be using a counter key later on. In this case, the key is going to be the actual word, and the value is going to be a 1. In reality, this value could be whatever, but for simplicity, let's use 1. And now we can do the count per key. Now the pipeline hasn't run yet, since we need a specific way of running this pipeline. We're using Interactive Runner, and Interactive Runner provides us with a specific way of doing this, which is IV show, and it gives us some extra visualization that you will see in some seconds. So if I do IV.show count, which is the variable we have here, we can see that the pipeline is running now, and in some seconds we will see the output of it. We can see that King appeared 243 times, And we can even see what was the word that appeared the most, which is the, not a surprise at all. So we have seen how to run a pipeline in interactive runner. Let's now move it to Dataflow. So we change the runner to Dataflow runner. And we need to add these options that we mentioned before. So we first need a project. Project is a variable that is already imported here. We're going to need a region for the workers to be in. So let's use US Central 1. We are going to need a temporary location, which is going to be a bucket and a folder called temp. And I'm going to add a name to this pipeline, which is going to be, I don't know, word count Beam day. So this is everything we need to reach Dataflow. And now we can see that the business logic remains the same. We don't need to change anything. And now we need to execute the pipeline. Before we were using IBShow, which again is something specific for interactive runner. So we need to modify this. So let's do pipeline equal peer1. Peer1 is the way of executing pipelines in Dataflow runner or direct runner also. So if we do this, the pipeline should start reaching GCP. And if I run this next cell, it's going to help us see the link directly to GCP. So the pipeline is reaching GCP. And if I click here, we can see our pipeline running in our GCP project using Dataflow runner. So you can see here that without changing our business logic, just by changing the options, we have reached Dataflow and the pipeline will work exactly the same. So let's see now how hard it is to change from batch to streaming. The first thing we need to do is to tell our options that we're using a streaming pipeline. So let's do a streaming equal true. And I'm also going to be changing the name to streaming. Let's run this cell now. Now, before we were using a bounded source, which is a public bucket. Since our pipeline is streaming now, we need something unbounded. So let's use one pub subtopic. So let's do read from PubSub and our topic, which is again imported in this cell here. When we read from PubSub, the output it's on bytes, so we need to decode those. So let's do decode. This is the name of our step, and I'm going to be using a map function, lambda b decode UTF-8. PubSub is an unbounded source, and since we're going to be aggregating later with count, we need to split this unbounded source into bounded pieces of data. In order to do that, we create one window that is going to split our data in chunks. So window into window dot, and I'm going to use a fixed window of, I don't know, 60 seconds. Yeah. So again, the pipeline hasn't run yet. We need to execute the next cells. So pipeline now should be reaching GCP, and in some seconds we will see the link that will take us to GCP. So now let's click here, and we're again going to GCP, and we will see our pipeline running in streaming. You can see it here, and the count is exactly the same. So you see that the only thing we needed to change was our source and adding this extra logic that we mentioned before, like a window, or in the case of PubSub, decoding the messages. But the actual word count, the actual part that we're counting, remains the same. So we didn't need to change the flat map. We didn't need to change the count per key. We only needed to change the source and adding this extra logic. So I hope you like this demo, and I hope you got the idea of the flexibility that Apache Beam has.
So thanks everyone. I hope you liked the presentation and I hope you got an idea of the flexibility that Apache Beam has, and hope you like the rest of the Beam Day presentations. Thanks and bye.
Thanks, Inigo. This is a great introduction to what Beam is and what it can do. What did you think about it, Robert?
I love that with cross-language, you get to use production-hardened transforms, even with newer SDKs like Go.
Yeah, that's a great thing about it, is that even if you're writing a new SDK, so if you wanted to make a JavaScript or TypeScript SDK, you don't have to go and implement all the different sources and sinks. So you can just use the production hardened transforms that have been living for a while in Java or Python with the new SDK. So next we'll hear from Boyuan Zhang with an introduction of building Beam IO using Splittable DoFn. Take it away.
Hello everyone, I'm Boyuan from Google Cloud Dataflow. Today I'm going to give a brief introduction about how to build source in Beam with Splittable DoFn. When we get into details, first I will introduce a little bit more on what is Beam source and what is Splittable DoFn. Most Beam pipelines are reading from external sources and get this output records from the source and do certain computations and write a computation result into sync. So take a word count pipeline as example. I have put the pipeline shapes on the right. So you can see that word count pipeline read the text file from external source and then get the each word from the text and do a count per word and write a result into the sync. So as you can see, mostly the Beam source will be the root node of the pipeline. And before we introduce Splittable DoFn into Beam, we already have bounded source API for batch pipeline and unbounded source API for streaming pipeline. So for example, in this case, the text IO is a bounded source. And for example, Kafka is a streaming source. Usually, when we read from bounded source, we want the read as fast as we can. So what we can do is we can have multiple parallelisms while we do the reading. So there are two kinds of splits. The first one is initial split, and the second one is dynamic split. Initial split will give us initial parallelisms before we actually reading. So still use a text IO as example. We have a text file, right? And we want to read that file. And if we know that we have two idle workers before we actually read, we actually can split the text into two shards, and we can have these two workers read from these two shards in parallel. Then we will have the read faster. And dynamic split means we want the split happens during we are doing the reading. And that split happens in the future. So this one will give us more parallelisms during we're doing the reading. So in order to do the dynamic split, we actually need a bounded source to do the initial sizing for the whole source. This will give a boundary and the size information of this source to the runners. This will help the runners to make the split decision. And during the reading, we also want the bounded source to be able to report the progress. That means we want the runners will need to know how much the bounded source has read and how much work left for that bounded source. It's also a useful signals for the runners to make a split decision. And finally, once the time that runners want to issue a split, the bounded source should be able to perform that split for the source and to gain more parallelisms. Usually for streaming, we actually are able to perform the initial split as well, but it's not really possible to do the dynamic split. It's easy to understand why we are not able to do so. It's because first, it's unbounded source. It doesn't have the boundary. And the second, because for the dynamic split, we usually want to split in the future. And it's not very know that for the unbounded source whether we will have the future. So usually we will not do that, but instead we will do the checkpoint for this source. And the most important things for unbounded source is we want the unbounded source to track the watermark correctly, especially when there are several downstream operations have a complicated windowing strategy and do the triggers on that. So that's very important for unbounded source. So given that we already have the bounded source API and unbounded source APIs for the Beam source, why we still want to introduce the new Splittable DoFn APIs into Beam? So the most important part for here is, as I mentioned, that based on our current framework, we should have the Beam source as a root node pipeline. Then we will have the use case like, for example, if I have two external sources, which is BigQuery and Kafka, and I store the topic partitions on the BigQuery, and first I need to know which topic and partition I can read from the BigQuery, and then read from Kafka. If I want to do all of the things inside one pipeline, then there's no way in current bounded source and unbounded source APIs to do, because it has to be the root node. But then with the Splittable DoFn, we are able to do so. So we can first read from the BigQuery, get a topic partition, and then let the read from Kafka to read from that topic partition and output records. The reason why Splittable DoFn can do so is because Splittable DoFn is a DoFn, and DoFn can be any nodes of the pipeline. And the second part is Splittable DoFn is a unified batch and streaming source model over Fun API execution. Fun API execution is a new execution model we introduced to Beam lately. It's kind of like a complicated concept, so I will not go into details in this slide, but I put a link related to that at the end of the slide. And the third one is we will have the ability to split for the Splittable DoFn. So that means we can provide both initial split and dynamic split for bounded source, so it's perfect for that one. And for more details about what split means, we will go into deeper in the following slides. And the last one is Splittable DoFn is a DoFn, right? So it will have a simple syntax as DoFn. And most Beam devs are familiar with DoFn, so it will be simpler and straightforward for them to build their own source on top of Splittable DoFn. And one more interesting thing around that is, if you are building your own source on top of Splittable DoFn, then all you need to do is have one implementation which should be work for both streaming and batch. Instead of in the unbounded source and unbounded source API, what you have to do is you have to write implementation derived from bounded source API for batch pipeline, and write another implementation derived from unbounded source API for streaming pipeline. That's kind of like it's burden for most developers to do two implementations for different purpose. So given that we already know that's why we want to have Splittable DoFn, then what is Splittable DoFn? So as I mentioned many times, Splittable DoFn is a DoFn with ability to split. So first, it's a DoFn. It will have the all simple syntax and attributes from DoFn. And the second, it will have the ability to be able to split inside one element. So what that means, split inside one element, let's look into small examples. So let's say we have two elements, element 1, element 2, and we have DoFn instance processing these two elements. And we happen to have the first element, element 1, is super huge and is heavy, and currently we are at 20% of it. So let's say for the following 80% of element, we still need to take one more day to process it. So if we are using a normal DoFn instance, what we can do is we have to wait for the first element to be finished and continues to process element 2. So it's slow and we have to wait a lot of time. But if we have a Splittable DoFn for that, what we can do is we can ask the first element to split. So that means we can say, I want you, first element, to split at the 50% of you. Then we will have the first half of the first element on the first Splittable DoFn instance, and then we can have the second half of the element 1 and the whole element 2 to be rescheduled on another instance. At this moment, we will have two Splittable DoFn instances working on these two shards in parallel. So that means we should have the pipeline to be much faster. So as you can see, it's very powerful and it's very useful for batch. Then, what we should think about when we building Splittable DoFn, the first one is the element and restriction. Usually, the Splittable DoFn is a DoFn, right? So it will take an input as element and output several records. So the element here is the input, and the restriction usually is a description to describe how much work inside that element. So taking an example, Splittable DoFn on the right as example. Let's say we have a string of A, B, C, D as input to that Splittable DoFn. And what this Splittable DoFn will do is it will output characters A, B, C, D separately. In this case, the element will be the input string, which is A, B, C, D. And if I'm writing this kind of Splittable DoFn, I will say I want to have a restriction which can describe how many works in this string. So I will take an offset range from 0 to 4 to describe that I have a string, and the index for this string is from 0 to 4. So that's element and restriction. And we also have a restriction tracker to track the progress of the restriction. And for a restriction tracker, you should know the current consumed position of the restriction and should know the progress and when it's time to do the split from the runners, and the restriction tracker should be able to do so. A simple example can be, let's say we still have this kind of DoFn, and we already output character A. So the current position is 1, and the work has been done is from 0 to 1, which I have output 1 characters. And the work of the remaining is from 1 to 4. That means I still have 3 characters left to output. Combining all of the information above, including what is bounded source and bounded source requires, and what Splittable DoFn can provide, now we can think about when it's time to build a source on top of Splittable DoFn, what we should think about. The first question is we should decide what is element and what is the restriction. It's important to pick up the suitable element and the restriction for your source because it will affect the implementation details of your source. And the second is we should consider what kind of split we want to support for our source. As we know that for bounded source, it's always good to have initial split and dynamic split. And for streaming, it's also always good to have initial split and to be able to do the checkpointing. And third one is for streaming specifically, is if I'm writing a source for streaming, I need to make sure whether I track and advanced watermark correctly. And I need to make sure I don't hold back the watermark incorrectly to affect the pipeline results. So the first question, what is the element and what is the restriction? So usually for source, the element can be the metadata of the source, and the restriction can be the description to describe how much work in this metadata. So taking text.io as example, for text.io, we can use file name as the element. For example, I want to read from file 1 text, right? And for the restriction, we can use a offset range from 0 to the total lines of the text as a restriction. So that will describe the whole work inside that file. And another example is reading from Kafka. We know that Kafka usually reads from topic partitions, and it will output records with offset. In that case, we can use topic partition as element, and we can also use offset range from 0 to infinity to describe the total workload inside for that topic and partition. Then it's time to think about whether we can do for initial split. So that means if we know that our source can do the initial split, it's always good to do so. If we have decided that we want to do the initial split, the only things we need to do is we can create a function in the DoFn and annotate the function with split restriction annotation. The SDK framework will pick up this function to perform initial split when it's time to do so automatically. So for example, we still use the text.io, right? So the element is a file name, and let's say we have timelines for that text file, and we want to read the text file one line by one line. So in this case, the restriction will be 0 to 10. And I already know that I will have 2 workers to be able to read from 2 shards in parallel from the start. So I can split the restriction from 0 to 5 and 5 to 10. And the runners, Before the read, the runners will redistribute these two shards on these two workers, and we will have the read on these two workers in parallel at the same time. During the actual reading happens, we should think about whether we want to provide more information to runner. That's progress. So in terms of progress, it always describes how much work we have been done and how much work has been left for this source. For batch, it's a useful signal to make a dynamic split decision, and for streaming, it's useful to let the runner know the backlog. Especially for Dataflow, Dataflow will use a backlog to determine whether to bring up more workers to work on the source. So that means if we can let the runner know we still have a lot of work to do, the Dataflow can bring up more workers, we will have our streaming pipelines faster. So for the progress, let's still use the TextIO example. So let's say we are reading the first shard of the text. So we have the file name as element again, and has the first shard, which is from 0 to 5. And let's say we have output the first line. So at this moment, the progress is kind of like the work has been done is we have output one line, which is from 0 to 10, which is from 0 to 1. And the work left is from 1 to 4, 1 to 5, which means we still have 4 lines to be outputted. And when the runners issue split, usually for batch, it's dynamic split to gain more parallelisms, and for streaming, it's usually checkpointing, which means runners want us to stop reading as soon as possible and return whatever we have to the runners. So for the dynamic split, let's say after we give the progress to the runners, and the runner says, I want you to split at 50% of the remaining element. So that means for the current remaining work, which is from 1 to 4, 1 to 5, the runner wants us to split at 50% of it. So that means in the current instance, we will still output line 2 and line 3, and we will return restrictions 3 to 5 to the runners, and the runner will have another workers to work on this shard to continuously to output line 4 to line 3 to line 4. So that means at this moment, we will gain more parallelisms and our pipeline should be faster. And for streaming, because runner wants us to stop reading immediately, that means after we finish processing output first line, we should stop and return the whole remaining restriction, which is from 1 to 5 to the runners. And the runners will have another workers to work on this shard. And finally, we are going to the streaming watermark set. As I mentioned, the watermark is extremely important for streaming pipelines, especially when your pipelines has complicated windowing strategy and triggers. So when we're building our source based on Splittable DoFn for streaming, we should especially care about the watermark. So for watermark, Splittable DoFn offers a utility class called Watermark Estimator for you to estimate the watermark from the Splittable DoFn. There are 3 common tabs for the watermark estimator: the wall-time, monotonically increasing, and the manual one. The wall-time watermark estimator is super straightforward. It will always use current processing timestamp as the output watermark. And for monotonically increasing, it will use the output timestamp from the records of the output of the Splittable DoFn. And it expects the timestamp from the output of the Splittable DoFn to be always increasing monotonically. If it doesn't, it will throw exceptions and errors from the SDK and says, I have errors and I don't want to output more records because it has execution errors. And for manual one, it gives the source author the freedom to set the watermark by themselves inside the Splittable DoFn method. You can set the watermark to any timestamp that makes sense to you, as long as you can make sure that timestamp is correct and it will not mess up the pipelines. So basically, that's all the things I want to cover. And because there are too many points of views of the Splittable DoFn and building source with Splittable DoFn, we don't get into details on each point, but hopefully this overall introduction will be helpful. And finally, I will attach more resources if you are interested here, which can help you to understand more when it's time to build your own source on top of Splittable DoFn. So first, if you are interested in building your own Splittable DoFn, you can look into our programming guide. So this guide will covers Python, Java, and Go SDKs. And if you are using open source runners such as Spark and Flink, and you are wondering what kind of functionalities these runners can support for Splittable DoFn, you can look into the capability metrics. And as I mentioned, for dynamic split, it's very complicated. And for Dataflow, we have a blog post to explain how this happens on Dataflow. It's very interesting and helpful. And if you're interested, you can look into this one for more details about dynamic split. And for Beam Fun API, we also have a centralized documentation to say what kind of execution models we want to have and all the different aspects for these models we have. And if you decide to build your own source, I would recommend you look into our Beam IO guide first to get a sense of how to build a kind of things and what things you need to prepare. And if you are interested in knowing how these ideas get generated at the first place, I would recommend you can look into our design doc website. It contains all of the design docs we have so far, and there are many interesting reading materials there. And finally, if you decide to contribute to the Beam or bring any your source or any your code into Beam, the first thing I would recommend is to look into our contribution guide. It includes all of the instructions, ideas on how to contribute to our Beam community. And finally, thanks for your interest and thanks for your time and welcome to Beam community.
Thanks, Boyuan. Splittable DoFn sounds like a great improvement on the model. It's neat that if you can define a way to restrict and split your data, Beam can make it work dynamically so runners can scale your pipeline as needed. What do you like about it, Sam?
Well, I think like the main point that I like is that it unifies all the different sources to work under a single abstraction. Right, this will help to increase the Beam source repertoire because, like I said previously, the custom source API was different for Python, was different for Java, and it led to all sorts of weird interactions in Dataflow and in the backend, kind of in general. So this, by using the Splittable DoFn, it should kind of help to harden the sources and sinks and to make them faster overall.
That's a very good point. For you in the audience, don't forget you can ask questions in the live Q&A forum and get responses from our speakers. Next, we'll hear from Alex from Akvelon about how they use Dataflow templates.
Welcome to Dataflow Templates. Today I'm going to share an example use case for Dataflow templates, how to create and execute Dataflow Flex templates, and how to get started contributing templates to open source community. My name is Alex Kasalapov. I'm program manager at Akvelon, a custom software engineering company, Google Cloud partner, headquartered in Seattle, Washington, with engineering offices in Europe and North America. Over the last 20 years, we helped over 100 clients to build software, data analytics, machine learning, enterprise, and mobile apps. I will share an example use case where Dataflow was a great solution for data transformation, and custom template helped to integrate external data protection service into pipeline. A customer use case was to ingest large volumes of data that included sensitive data like credit card or PII, and a third-party data protection service was used for tokenization, converting data elements like credit card number into non-sensitive token representations that can be stored safely. Based on access role, a user may see a token representation of data, a partially masked data, like last 4 digits of credit card number, or an original credit card number. Dataflow provides an auto-scaling, fully managed, high-performance data transformation service with consumption-based pricing that was perfect fit for data processing. Challenge was that out of box, there was no support for external calls to third-party service to tokenize data. A custom pipeline has to be built to support this, and different input and output options need to be supported. On Google Cloud Storage, we had JSON, CSVs, Avro, we had data from PubSub, and also pipeline had to support different output syncs, BigQuery, Bigtable, GCS. So this variety of options on the I/O side that required a same pipeline to do same processing. Templatizing pipeline allowed to implement pipeline just once and support all required I/O options using template parameters. To implement tokenization, we created Dataflow pipeline with processing logic to call external REST service. We had several challenges to solve, including optimizing communication with REST service for performance. Stateful DoFn Beam feature helped us to buffer and batch data into bundles that worker can send in one request and even maintain ordering of data in these batches. Then we packaged pipeline into template, and that enabled us to support different input-output sources, execution parameters, and share template easily. Next, we will look how to get from a pipeline to Dataflow template. What is a pipeline? A pipeline is a flow of operations in Beam. In simplest way, it starts with I/O read, data transformations are applied, and finally, I/O write transform is applied to output data into output sync. Dataflow templates is a way to package and stage pipelines. It has 2 phases. Template construction is implementing pipeline, compiling it into execution graph, and staging on Google Cloud. Execution phase allows to run templates using Google Cloud Console, gCloud Tool, or REST API without development environment, without configuring associated dependencies on your computer. Runtime parameter allows to customize execution of the pipeline. Running your pipeline does not require you to recompile code every time. There are 2 template types. Classic templates are staged as permanently fixed execution graphs on Google Cloud Storage. Classic templates require Beam pipeline code modification to implement value provider interface to defer reading of variables until template is run. For example, name of PubSub subscription that user might want to pass at execution. A minor change in option will require recompiling template by developers, for example, to change to Google Cloud Storage instead of PubSub. Flex templates package an existing Beam pipeline as a Docker image on your project's container registry and create template specification metadata on Google Cloud Storage bucket. To execute Flex template, then just refer to the template spec file. Benefits of Flex templates are dynamic execution graph that is constructed and validated at job launch time based on final parameters that user supplied. Flex templates eliminated need for value provider interface, improving developer experience. Creating Dataflow Flex template has 3 steps: implement data pipeline, create metadata, and build the template. Pipeline for Flex templates can be implemented in Java or Python. I'm going to switch to my demo example that shows our tokenization pipeline. Tokenization pipeline was implemented in Java. Beam pipeline in Java has main method as an entry point for pipeline execution that often processes options and calls pipeline run method that implements transforms and other business logic for the pipeline. Next, Beam pipeline is compiled into Uber file that contains all dependencies using Maven or Gradle. And next step to get from pipeline to template is using gcloud Dataflow Flex template build command that will create Docker container, metadata file, and stage them in Google Cloud. I'm going to switch to my demo environment and start this process. Here, I'm going to start Maven compile process. And just to verify that it started, it's going to take a little while to complete. And while it's compiling, I'm going to switch to metadata file and provide an overview what it is. Template metadata file provides template name, description, and parameters that user can specify when creating job from template in Web Console, in gcloud, or REST API. Template parameters have name, label, help text, param type, properties, and also can be optional or required, and support regular expression validation of user input that comes really user-friendly when a job is created in Web Console. Maven build just completed, and we can switch to the second step of the template build. The second step is running gcloud Dataflow Flex template build. I will start it right away and will explain what I have on the screen. I use environment variables to help organize my commands and scripts. So I have project ID, storage and template path, Google Container Registry, image path, and base container image as an environment variable. When I start the Flex template build command, I provide template path where metadata will be stored. I specify container image path and SDK language that Beam pipeline is using. I also specify base container image, one of the Google provided images for Dataflow containers. And lastly, I specify some source files. Source for metadata, source for Uber jar file that we just completed in previous step, and specify main class that will be called when Dataflow creates job from this template. I'm going to pause here for this command to complete. Flex template build just completed. I'm going to navigate to Web Console to verify container registry and metadata file. In my project's container registry, I just go inside of the path and the image has just been uploaded. Next, I'm switching to template path that was used for metadata file and validating that tokenization demo JSON metadata file has been created and completed. We can go in and actually check the JSON. It has reference to Docker image, metadata, and down at the bottom, it has SDK info that specifies template language. We are ready to run the template in Dataflow. I'm going to navigate to Dataflow and here create job from template. In this dropdown, I can select different templates, and there's many templates that come from Google with Dataflow. For this project, we created custom template, and I will select custom template and navigate to cloud storage to select template metadata file. You notice that description of the template that you can see here just changed to the template we created. And now I will provide required parameter with JSON schema, with data schema for my input, and expand optional parameters to specify other templates that I will need for the demo. Path to input data, format of the input files, and I'm gonna put JSON with a typo just to demonstrate how validation works. It allows me to easily notice a typo, go back and fix it, and continue with other parameters for my demo. REST endpoint for tokenization, mock service that we use. And next parameter is payload configuration that defines which fields, which data elements I want to tokenize. Template also supports dead letter path that we can specify to store any errors in data processing on Google Cloud Storage. And lastly, I will use BigQuery table as my output and will specify table here as a parameter. When we scroll down, we see all the data flow parameters that all Dataflow jobs support. We can also specify any of those parameters with a custom template. I'm going to stick with defaults, and now we'll click Run the job to create Dataflow job from this custom template. It will take a moment to analyze the job and create execution graph. Next, the job will be staged and executed. It might take a few minutes, and I will demo result of running this job that I did before the demo. When job is created from custom template, job execution graph will be constructed based on data processing in the pipeline that was implemented. You can see DSG tokenization is one of the transforms here, and also we're gonna write successful transforms into our output, and we have error handling transforms that will catch any errors. When the job is run, the output will be stored in BigQuery table. Switching to BigQuery, I used demo JSON GCS to BigQuery as a table for output. The table was created by Dataflow job, and table schema matches input schema of the input data. When I click on preview, I will see a snippet of the output data. Here you can see that SSN and last name columns have been tokenized and some randomly looking data is stored in the table. This is exactly what we wanted to see as a result. Now we built and ran Dataflow Template. You can build custom Dataflow Flex templates for your projects and easily share them with users to create Dataflow jobs that they need. You might also be thinking, how do I share template with open source community? To share templates with community, you might contribute them to Dataflow Templates repo. It's Google Cloud repository, and templates from Google and other open source contributors are stored there. It's easy to get started with contributions. Fork repository to develop your template. Develop pipeline following style guides and best practices provided by Google. Sign contributor license agreement and submit template pull request to merge it. Pull request will go through code review and will get merged with Dataflow templates. Summarizing today's session, key takeaways are Dataflow Flex templates are containerized packages with all necessary environment to run Dataflow pipeline, so users can create job from template in Cloud Console, gcloud command line tool, or REST API. Flex templates use dynamic execution graph, creating and validating job execution graph with final user parameters when job is launched. Flex templates are more portable, easier to support with input and output options. And we also learned how to create, build, and run Dataflow Flex template. Thank you for joining Dataflow template session. Reach out to us at Akvelon if you're interested in building Google Cloud solution with Dataflow or Apache Beam for your use case.
Thanks, Alex. That was a great overview and introduction. Before templates, it was pretty difficult to be able to productionize data flows, right? You had to manually have your own environments for both Python and Java, and then kind of compile those independently and have some sort of workflow in order to work with the Dataflow API to submit them over time. But with templates, everything is pretty self-contained within the UI, where you can just submit your code to the service, and then it'll automatically wrap things up for you into this Flex template, where you're even able to schedule things at some distinct intervals over time. What did you get out of it, Robert?
Well, the ability to bring your own Docker containers with the Flex templates sounds super useful.
Yeah, that is very true. I know a lot of customers that we've seen, they like to customize their own Docker containers, maybe use different operating systems, maybe don't necessarily like the update cadence for Apache Beam and want to do more frequent updates to the libraries. So it allows a lot of flexibility. So next we'll hear from William Sykes about building Beam pipelines with CDC and Debezium.
Hey Beam community, Will from Wiseline here to talk about Apache Beam, change data capture, and p-transforms. Over the last 2 years, Wiseline has been involved in several Apache Beam related initiatives. During the Apache Beam User Experience Research Project, Wiseline identified pain points, learning gaps, and opportunities to improve the adoption of the Apache Beam platform. Wiseline was able to provide a comprehensive list of actions to improve the Apache Beam platform. The CDC and Debezium project. This is the focus of today's topic. This project was executed in 6 weeks and the final product was merged in the community. We're also actively involved in Beam SDK and infrastructure work. Wizeline is working on some enhancements to the core Beam SDKs. These contributions are crucial in easing the adoption of Apache Beam as a solution. Now a little bit about change data capture. Change data capture, or CDC, is a term for a system that monitors and captures the changes in data so that other software can respond to those changes. As some organizations have grown, they have the need to pull data from a single source and distribute it to many different applications. For example, identifying changes in the database and sending them to both an ERP and CRM system. Traditionally, data warehouses required custom CDC support to manage sync with the upstream OLTP databases. These solutions were custom and cumbersome to manage. Two primary types of CDC include trigger and log-based. And there are a variety of commercial CDC vendors available in the market today. Debezium, the open source offering, is essentially a modern distributed change data capture platform that supports monitoring a variety of database systems. Debezium is an open source project that provides a low latency data streaming platform for change data capture. You set up and configure Debezium to monitor your databases, and then your applications consume events for each row level change made to the database. Only committed changes are visible, so your application doesn't have to worry about transactions or changes that are rolled back. Debezium provides a single model for all change events, so your application does not have to worry about the intricacies of each kind of database management system. Additionally, since Debezium records the history of data changes in durable replicated logs, your application can be stopped and restarted at any time. It will be able to consume all of the events it missed while it was not running, ensuring all data are processed correctly and completely. As of now, MySQL, PostgreSQL, SQL Server, and DB2 are all capable of using CDC with Beam. Now I'm going to talk a bit about the motivation for this work. The primary motivation for this project was to add CDC functionality to Apache Beam. The commercial offerings are expensive and are often closed, restricting the developers and data engineers from building creative and efficient systems. Before the Debezium I/O, Beam users that wanted to consume change data streams from databases needed to take on one of the following architectural dependencies: Kafka by deploying Debezium, PubSub and Data Catalog by deploying a custom connector, or other commercial connectors. By developing a p-transform that provides this functionality directly in Beam without any additional architectural requirements like Kafka or PubSub, users can get started consuming change data streams from their database. Here you can see how using the Debezium I/O reduces complexity in the architecture. It's important to note that this architecture can run in parallel with your existing Kafka implementations. Here are some details about the solution Wizeline developed. Debezium connectors are implemented as a Kafka source connector that splits into a single source task. Wizeline developed a Debezium I/O transformer as a splittable DoFn that reads from a variety of SQL sources using Kafka source connector and converts the read source record into a P collection in JSON format. Using the existing Kafka source connector, Debezium I/O spreads out CDC data in a Kafka record format or source record. These records will be processed by the new splittable DoFn transformer to place them in a Beam-friendly format, JSON, inside a P collection. This P collection will be used in the subsequent P transform. Now a bit about the flow of events. Beam lets you easily create data pipelines by connecting what they call transformations. Each transformation delivers a collection of something, in this case, records to the next transformation. Then the last transformation does the same, and so on. Now let's focus on the transformations. The pipeline has 3 important steps. In step 1, the Debezium I/O, or read transform, reads and captures the CDC events, then converts the Kafka source record CDC event into a JSON element. In step 2, the JSON to table row transformer will take that CDC event as JSON and transform it into, in this case, BigQuery's table row collection. Finally, in step 3, the write transform will push out the resultant rows to BigQuery into the specified output table. Here's a bit about Wiseline's engagement process. First, we gathered input from the Apache Beam community. We identified that CDC could be implemented in Beam via Debezium. Artifacts were created in UML to validate our understanding. We then kicked off our 6-week development phase using agile methodologies. We conducted periodic code reviews with the community and contributed via unit and integration testing. After final review, we were able to push the code to the community. Now we're going to take a brief look at the code. We are looking at the latest Debezium io.java file in the Beam repository. Here, Debezium IO declares its readT class function, which extends from a p-transform. Here we see the overridden expand function. On line 213, a Kafka source consumer function is instantiated, passing the configuration, format function, and some other restrictions. The Kafka source consumer function is a splittable DoFn used to process records fetched from supported Debezium connectors. Now we're going to review Kafka source consumer process function. Kafka source consumer process function passes configuration and instantiates the Kafka source connector. On line 155, the connector instantiates the Kafka source task, which controls the execution of the connector. On line 161 and 162, we initialize and start the task. On line 164, record polling begins Kafka source record from the connector's internal queue. The Kafka source record is then passed by the configured map function to transform it into a JSON representation, which is the return type of the P collection. Now I'm going to show you how to stand up a very simple pipeline using Apache Beam, Debezium, MySQL, and GCP. Here's a very high level of my environment. I'm using a development workstation running Debian 10 and Maven and some other minor dependencies. For testing, make sure this environment has correct access to both source and target. I have a MySQL database via Docker image as my source. These test Dockers are available in the Debezium repositories. I'm using BigQuery as the destination for MySQL data after transformation. The first thing I'll do is configure my data source. In this case, I'm using one of the Debezium example MySQL containers, version 1.3. The example MySQL Docker has a very simple schema that is perfect for testing. When considering your test setup, you should make sure that TCP port access is available from your source to target sync. The Docker command defines the database connection parameters which will be used in standing up the pipeline in later steps. Now let's set up BigQuery. Log into GCP. From the BigQuery Explorer, browse to your dataset and create a new table. Under Schema, click Add Field, and under Name, enter JSON. Let's prepare the pipeline configuration on the development workstation. We are viewing step 1 in the project.java file. In this case, it's one of the samples provided by Debezium. Here, step 1 defines the Debezium connector configuration. The connector configurations contain options, class, and property references. These are the options that will be passed at the command line with Maven. Let's take a look at steps 2 and 3. In step 2, the I/O transforms the JSON into table row. And in step 3, the table row data is appended to the BigQuery output table. Now let's kick off the pipeline. In order to do so, we need to stage our Maven command. This command defines the template, data runner, Google project, source JDBC connection info, and more. Notice the BigQuery temporary directory. This will need to be configured prior to testing. After the Maven command is set up, I will launch the pipeline. You will see the pipe building on the bottom of the screen. Now I will log into GCP Dataflow on the right. You will notice the Dataflow job up and running. Let's check BigQuery to see if we have data. We do have data. If you analyze the logs, you can see verbose information about the pipeline and the transformations occurring. You may have the need to convert strings of data in some manner before they land in the target. For example, your pipeline might receive a date value in PST and you would like to convert it to UTC at your target. This is possible with this technology. Within the pipeline logging, you can see the before and after value of the data as it transfers the pipeline. One thing to test is to make an insert at the source to see if it populates BigQuery. That wraps up my quick demo. I hope that after going through this with me, you have a better understanding of Wiseline's contribution to Apache Beam. Developing pipelines using Apache Beam allows organizations many benefits, including data portability, flexibility, and scalability. Wiseline is actively working on Apache Beam related projects and will continue to contribute. I have added some links at the bottom of this document if you would like to learn more. Thank you, Apache Beam community, and have a good day.
Thank you so much, William. Avoiding extra event infrastructure just to get your own data sounds like a huge win.
So Robert, I didn't really fully understand how CDC can be useful. So I understand that it's this way of being able to track updates to a database, right? So you can like subscribe to updates, like inserts, deletes. But how does that really help me?
Well, it's about making sure that your data and your analytics match up. If you don't have, if your source, if what you're doing your analysis over isn't actually based on the source of truth, your database, you're going to have drift over time and you're going to end up with lots of discontinuities in your graph and you'll have to spend more compute recomputing everything.
Oh, okay. So basically in a normal streaming pipeline, right, you're doing real-time analytics, but those analytics are streaming in directly from the source, right? They're not being journaled anywhere.
That's right. Well, they are being journaled. They're just being journaled and sent out by the database itself, and that's what Debezium gives you.
Oh, okay. So it gives you kind of like that extra layer there, that extra layer of safety.
That's right.
Okay.
And with that, it's time for the after party. Come and join us at the after party by clicking the Watch Live button on the event's agenda page to be redirected to Google Meet.
So today's speakers will also be joining us, and we will have some quizzes, interactive activities, surprise guests, and maybe some swag. Well, do you think there'll be some swag?
I think I know there's going to be some swag. We'll hope to see you there. Thank you.
Thank you.